Okay, it's recording, so you can talk about it now.
Gone all shy.
Play the video.
Okay, let's talk about forces inside the nucleus. Who knows a force inside the nucleus? Before that. It's negligible. Before that. Yeah, electrostatic. So we've got all these charged particles, right? We've got these protons inside the nucleus. And so what we know from like a long time ago is that they have a repulsive force between them. And we call it the Coulomb repulsion. So Coulomb repulsion acts between the protons, and we know that because we've got these protons into a really, really, really small volume, that's made the size of that force absolutely enormous. And so we've got this huge force acting, trying to push these protons apart. But what we know is that they don't burst apart. And so that's why we need the force that Alex mentioned before, the nuclear strong force, in order to hold that nucleus together. And so the nuclear strong force acts between all of the nucleons in the nucleus, but it's a kind of nearest neighbours only force. And so if we think about this neutron here, it can only exert that force on particles that it's in contact with. And the nuclear strong force is a lot like a rubber band, that actually as we increase the distance between those particles, the size of the force increases. But like a rubber band, beyond a certain point there's a snap and then the force goes to zero. So the nuclear strong force is like that, in that as we move those particles further apart, it gets stronger, not weaker, counterintuitively, but that beyond a certain point it goes to zero. Okay, so there it is, in black and white, what we talked about. And when we're thinking about how stable a nucleus is, what we notice from looking at the periodic table is we generally have a similar number in our stable nuclei of protons and neutrons. Often just a few more neutrons than what we do protons. And we notice that difference getting greater and greater as we move up the periodic table, so that when we get to an element like uranium, say, we end up with 92 protons and 140 something neutrons, so quite a lot more neutrons than protons. And that balance of how many protons and neutrons we've got is what dictates how stable or unstable a nucleus is. So if we've got too many or too few of either of those, that's going to lead to the nucleus being less stable, and it will tend to decay to a more stable state. And so when we think back to our binding energy per nucleon, the nucleus will always tend to decay from a state of lower binding energy per nucleon to higher binding energy per nucleon. And release energy in the process. We call that. Next time we're going to have a look at a graph of binding energy per nucleon against nucleon number.